Welcome to our session on HVAC systems. Today, we will explore the vital role HVAC systems play in ensuring comfortable, healthy indoor environments by regulating air quality, temperature, and humidity. We'll also discuss the energy efficiency, low maintenance benefits, and advancements in technology that make modern HVAC systems a smart choice for facility owners and managers. Let's dive into how these systems enhance comfort and performance in various settings. First, let's discuss the introduction to HVAC systems, which are critical components for creating comfortable and healthy indoor environments. Now, let's break down what HVAC stands for: heating, ventilation, and air conditioning. Each of these functions plays a unique role in maintaining a balanced and controlled indoor climate. HVAC systems filter and clean the air we breathe, removing harmful pollutants, allergens, and contaminants. This is vital for maintaining good health, particularly in healthcare settings where recovery can be significantly influenced by air quality. Next, these systems are designed to regulate indoor temperature and humidity. A properly functioning HVAC system maintains the perfect balance, enhancing not just comfort but also productivity and overall well-being. Lastly, let's talk about how advancements in technology have revolutionized HVAC systems. Many modern systems now integrate smart features and automation, enabling precise control and real-time monitoring. Basics of HVAC system explained in this diagram. This diagram illustrates the key components and processes of an HVAC system. First, boilers and heaters supply hot and cold water, respectively, which are transported to the air handling unit coil through pumps. These components ensure the system can heat or cool air as needed. The dual piping system carries either hot or cold water, depending on the climate. This flexibility allows the system to adapt to varying conditions efficiently. Fresh air intake brings in outside air through filters, which remove dust and pollutants to ensure clean air enters the system. In the air treatment phase, the fresh air passes over the AHU coil, where it's either heated or cooled based on the water temperature. Finally, in the ventilation stage, the treated air is distributed throughout the building to maintain the desired temperature and air quality. This process demonstrates how HVAC systems manage indoor environments effectively, ensuring comfort and air quality. 7 HVAC processes: heating, cooling, cleaning, dehumidifying, humidifying, ventilating, air movement. Let's discuss the 7 key processes of an HVAC system that work together to create a comfortable and healthy indoor environment. First is heating. This process increases the indoor air temperature, providing warmth during cold weather. Boilers, furnaces, or heat pumps are typically used to generate this heat. Next is cooling, is another essential process, where the air temperature is lowered during hot weather for comfort. This is achieved using air conditioning systems or chilled water systems in the HVAC unit. Cleaning. Filters and air purifiers are used to remove pollutants, allergens, and particulate matter from the air. This significantly improves indoor air quality. Now, on to dehumidifying, which reduces excess moisture in the air. This is especially important in humid climates, as it creates a healthier environment and prevents issues like mold and mildew. Humidifying adds moisture to the air, which is crucial in dry climates. It prevents issues like dry skin, irritation, and static electricity. Ventilating is the process of bringing in fresh outdoor air while expelling stale indoor air. This maintains healthy oxygen levels and reduces indoor air pollution. Finally, air movement ensures proper circulation throughout the building. It evenly distributes treated air and removes stale air, maintaining a fresh and pleasant environment. Let's talk about how climate and the time of year affect HVAC systems. In colder regions or during winter, the focus shifts to heating. This process keeps indoor spaces warm and comfortable when outdoor temperatures drop. On the other hand, in hot and humid climates or during summer, the system works hard on cooling and dehumidification to maintain comfort and prevent excess moisture. Now, in temperate regions, the natural balance of outdoor conditions might reduce the need for heating or dehumidification. But one thing that remains essential in all climates and seasons is ventilation. It ensures fresh air is circulated indoors, which is vital for air quality. This illustration demonstrates the operation of a heating, ventilation, and air conditioning system HVAC, during both summer and winter seasons. In the summer section, we see how outside air is drawn into the system, where it is cooled before being circulated into the living space. The cooled air is regulated by the thermostat, ensuring a comfortable environment inside. Conversely, in the winter section, the process reverses, outside air is brought in and heated before it enters the home. This heated air is also managed by the thermostat to maintain desired indoor temperatures. The diagram highlights the system's versatility in providing both cooling and heating, adapting to seasonal changes to enhance indoor comfort throughout the year. Components within an HVAC system. As you may know, there are numerous combinations of components and configurations when it comes to HVAC systems. Each setup is designed to meet specific needs and environments. However, in this course, we'll be narrowing our focus to the main types of HVAC systems that are commonly used in residential, commercial, and industrial settings. Not only will we explore the different types, but we'll also dive deeper into how these systems work. We'll break down their energy efficiency, examine their advantages, and discuss the disadvantages so you can understand their practical applications. HVAC Components Overview. Let's quickly go over the main parts of an HVAC system. First up is the source. This is where the heating, cooling, or air treatment starts. For heating, we use boilers, furnaces, or heat pumps. For cooling, air conditioners and chillers are common, and fresh air comes in through filters and air purifiers. Next is distribution. This is all about moving that treated air or water to where it's needed. Ductwork helps circulate air, piping systems move hot or chilled water, and fans and blowers make sure everything flows smoothly. Then we have delivery. This is how the air or water reaches the spaces. Air diffusers and grills spread air evenly, radiators deliver heat, and VAV boxes help control airflow in specific areas. Finally, control keeps everything running efficiently. Thermostats monitor and adjust temperature, sensors track humidity and air quality, and control panels manage the system automatically. So, these four components: source, distribution, delivery, and control work together to create comfortable, clean, and energy-efficient indoor spaces. Let's talk about the source components in HVAC systems. These are the key elements that generate heating or cooling to keep indoor spaces comfortable. First, we have furnaces. They generate hot air for heating and usually use natural gas, oil, or electricity to produce heat efficiently. Next are direct expansion coils. These are responsible for directly cooling the air. They use refrigerants that absorb heat from the air and release it outdoors through a heat exchanger. Then there are boilers. They produce hot water or steam for heating, which is then sent through pipes to warm the air using radiators or air handling units. We also have chillers. These create cold water for cooling, which is either sent to spaces directly used to condition air before distributing it. Finally, cooling towers work with chillers to release heat from the system to the outside air, helping maintain energy efficiency especially in larger HVAC setups. These source components are the backbone of any HVAC system, ensuring temperature regulation in buildings. Now let's move on to distribution components in HVAC systems. These are the parts that move heating and cooling from the source to the spaces we occupy. First, we have pumps. They circulate hot or cold water, even steam through the system to ensure the heat or cooling reaches the right areas. Next are pipes. These carry the heated or chilled fluids throughout the entire system to deliver temperature control where it's needed. Then we have coils, located in air handling units, fan coil units. They're responsible for transferring heat to or from the air, depending on whether we're heating or cooling. Valves are another important part. They regulate the flow of hot water or steam, adjusting temperature as necessary. We also rely on fans to push air through the ducts and ensure even distribution of warm or cool air into the space. Dampers are used to control the airflow within these ducts, allowing precise temperature and airflow adjustments. Together, all these components maintain a consistent and comfortable indoor environment by delivering the right amount of heating or cooling to every space. Delivery components. Next, let's look at the delivery components in HVAC systems. These are the elements responsible for bringing heating or cooling directly into the spaces we occupy to maintain the desired indoor climate. First, we have diffusers. They spread air evenly throughout a room to ensure uniform heating or cooling. Then there are baseboard radiators. These are placed along the edges of walls and provide heat directly to the surrounding air. We also have fan coil units. These combine heating or cooling with a fan to circulate the air, making them efficient for temperature control in individual spaces. Finally, there are terminal devices. These are specialized components that deliver warm or cool air or water to specific areas as needed. All these components work together to ensure that the heated or cooled air or water is evenly and efficiently distributed, helping regulate temperature, humidity, and overall comfort. Control components. Now let's talk about control components in HVAC systems. These are the parts that manage how the system operates to maintain comfort, efficiency, safety, and save energy. First, we have input devices like thermostats and sensors. They gather important information about temperature, humidity, and air quality in the space. Next are the controllers. These process the data collected by sensors and send commands to adjust the system as needed. Then we have actuators, which are the devices that respond to these commands by adjusting valves, dampers, or fans to regulate airflow or water flow. Control components can either be manual or automatic. Today, they're often integrated into a building management system to optimize operations, improve energy usage, and reduce labor costs. All these elements work together to ensure the HVAC system operates efficiently while maintaining indoor comfort and safety. HVAC systems. Let's explore the main types of HVAC systems and how they differ. All air systems. Air and water systems. All water system. Let's take a closer look at all air systems. This system uses air as the primary medium for both heating and cooling. The diagram shows the key components, starting with cooling and heating coils that condition the air. Hot water circulates through these coils to either heat or cool the air as needed. The supply duct fan pushes this conditioned air through a humidifier to maintain optimal humidity levels before delivering it to the designated spaces. Meanwhile, exhaust fans ensure that stale or excess air is removed when necessary. Dampers are used to regulate airflow, adjusting based on climate changes or indoor air quality needs. All these components work together in an all-air system where air is the sole medium for both heating and cooling, providing efficient and effective climate control. Now let's explore air and water systems. In this system, chilled water is produced centrally and circulated to different areas of the building to cool the air. This chilled water flows through pipes and interacts with fan coil units, air handling units to cool and condition the indoor air. The main advantage of air and water systems is their ability to precisely control temperature and humidity levels because the chilled water is centrally produced. This also makes the system energy efficient by optimizing the cooling process across the building. Furthermore, these systems often work together with all air systems to maintain comfortable and stable indoor conditions throughout the space. Next, let's look at the all-water system. This system uses water as the only medium for both heating and cooling. Supply water is pumped into the conditioned spaces, and this water flows through coils in units like fan coil units, air handling units. The system uses flow valves to regulate how much water circulates, based on the specific heating or cooling needs. After circulating through the coils and either heating or cooling the space, the used water returns through return pipes. To maintain efficiency, the returning water passes through pressure-reducing valves that help balance the system's flow. This method is highly efficient because water has a higher thermal capacity, making it great for precise temperature control. Now let's compare central HVAC systems and unitary HVAC systems. Central HVAC systems are designed for large buildings with multiple zones. They use a central unit to condition the air, and the treated air is distributed throughout the building using ductwork. These systems are great for managing different climate needs across large spaces and are easier to maintain because they involve fewer smaller components. On the other hand, unitary HVAC systems are smaller, self-contained units. They're compact, cost-effective, and ideal for smaller buildings or spaces with simpler climate control needs. Each unit handles its own heating or cooling for its specific area, giving localized control. However, they require more frequent maintenance since there are multiple units to maintain. Both have their pros and cons depending on the size of the building and specific needs. All air systems. Let's talk about all air systems. An all air system uses only air as the medium for both heating and cooling. The process is straightforward. Cold air is supplied to spaces to cool them, and heating is achieved by adjusting the temperature of the same airstream using a heating coil central equipment. The air is usually conditioned at a central plant and then distributed to different zones through ductwork. What's unique about this system is that it doesn't rely on chilled water or refrigeration like air-water systems. Instead, it uses only air to maintain temperature control across the building. This system is common in many applications where simplicity and centralized air distribution are key. Now let's look at the advantages of HVAC systems. First up is economic use and heat recovery. HVAC systems are great at recovering heat and redistributing it within the building, which helps reduce overall energy consumption. Next, winter humidification and handling outdoor air. HVAC systems can control humidity levels, especially during the colder months, and manage large volumes of outdoor air for ventilation purposes. Another advantage is control of temperature and humidity in zones. Zoned HVAC systems allow precise climate control in different areas of a building, improving both comfort and energy efficiency. We can also talk about improved air quality and smoke control. HVAC systems filter and clean the air, which enhances indoor air quality and offers smoke control during emergencies. Finally, there's the simple seasonal changeover. Many HVAC systems can smoothly switch between heating and cooling without complex adjustments. This even allows one zone to be heated while another is cooled at the same time. These features make HVAC systems efficient, comfortable, and versatile for modern building needs. Disadvantages of HVAC systems. Now let's examine some disadvantages of HVAC systems. First is high energy consumption. HVAC systems require large fans and motors, which can lead to significant energy use especially in bigger buildings. Next, increased building height due to ductwork. Central systems often require extensive ductwork, and this can add to a building's height and, in turn, the construction costs. Another issue is air balancing challenges. Achieving even airflow and maintaining consistent temperature control can be tricky, particularly in large spaces with multiple zones. We also have comfort issues in very cold climates. HVAC systems may struggle to maintain comfortable conditions when extremely cold air infiltrates the building. Finally, maintenance access coordination. The complexity of large HVAC systems, especially central ones, demands careful planning to ensure proper maintenance and timely system checks. While HVAC systems have many benefits, these challenges are important to consider during design and operation. Duct configurations. Now let's take a look at the different duct system configurations used in HVAC systems. These configurations depend on the building's needs and offer different benefits. First, we have the single duct system. This is the simplest design, where one duct serves both the supply and return air. It's straightforward and cost-effective but has limited flexibility. Next is the dual duct system. This system uses separate ducts for hot and cold air, allowing better temperature control across different spaces. It's great for maintaining different conditions in zones with varying needs. Lastly, we have multi-zone systems. These systems use multiple duct zoning systems, giving independent temperature control in different parts of a building. This design improves efficiency by only conditioning areas as needed. Each configuration has its own purpose, depending on the space, energy efficiency goals, and climate control requirements. Single duct systems. Let's now talk about single duct systems. A single duct system is one of the simplest and most cost-effective HVAC designs. It uses a single duct to handle both the supply of conditioned air and the return air. This design works well in buildings with uniform heating or cooling needs across the space. Because of its simplicity, it's a great choice for smaller buildings where advanced zoning isn't necessary. However, it's important to note that it doesn't provide independent zone control, so different areas can't be heated or cooled independently. In short, single duct systems are efficient and budget-friendly but best suited for spaces with similar climate control needs throughout. Dual duct systems. Now, let's explore dual duct systems. A dual duct system uses two separate ducts, one for hot air and one for cold air. This design allows for more precise temperature control in different areas zones of a building. These systems are especially useful in large buildings where different spaces may have varying heating or cooling needs. For example, one part of the building might need heating while another requires cooling, and a dual duct system can handle this simultaneously. While they offer excellent flexibility and comfort, they can be more complex and costly compared to simpler systems. Overall, dual duct systems are a smart choice for larger buildings with diverse climate control needs. Multi-zone systems. Next, let's talk about multi-zone systems. A multi-zone system uses separate ducts zoning systems to control heating and cooling independently in different areas zones of a building. This means each zone can have its own temperature setting based on its specific needs. The system adjusts airflow based on demand, only providing heating or cooling to spaces that are occupied require it. This not only enhances comfort but also makes multi-zone systems very energy efficient by reducing energy waste in unoccupied areas. Multi-zone systems are a great choice for large buildings with varied temperature needs across different spaces. They provide flexibility, efficiency, and better climate control overall. Now let's discuss zoning. Zoning involves dividing a building into separate thermal zones, and each of these zones has its own thermostat. This allows the HVAC system to maintain precise temperature control in different areas of the building based on individual needs. By implementing zoning, systems like single duct and dual duct systems can adjust their operation for each zone independently. This not only ensures occupant comfort but also optimizes energy usage by conditioning only the areas that are occupied in use. Zoning is a smart way to save energy and create a more comfortable indoor environment for everyone. Let's now look at single duct single zone systems. This type of system serves just one space, one specific thermal zone. It typically uses packaged air conditioning units that are simple to install and maintain, making them cost-effective and efficient for smaller spaces. An added benefit is that some single-duct single-zone systems can include heat recovery mechanisms, which improve energy efficiency, especially in climates with significant temperature changes. These systems are a great option when you're focusing on conditioning a single area with minimal complexity. Pressure balancing outdoor air. Next, let's explore pressure balancing outdoor air. Outdoor air is essential for proper ventilation, but it needs careful management to ensure a comfortable indoor environment. This system works by balancing the intake of outdoor air with the exhaust and return air. Proper pressure management prevents unconditioned air from sneaking into the building, which could lead to drafts, humidity issues, and pollutants. By balancing pressure, HVAC systems ensure consistent airflow, improved comfort, and better air quality for occupants. This diagram illustrates various air pathways in a typical house, highlighting how air moves in and out of the home. Arrows indicate airflow from multiple sources, including vents from the bathroom and kitchen, recessed lights, and the attic hatch. Each of these points can contribute to the overall ventilation of the house. Additionally, we see areas where air is leaking into and out of the house, such as through electrical outlets, the dryer vent, and the plumbing stack vent. The crawl space and outdoor faucet also play roles in this airflow dynamic. Understanding these pathways is essential for optimizing indoor air quality and energy efficiency, as managing air leakage can significantly impact heating and cooling costs as well as overall comfort. Pressure balancing exhaust air. Balancing exhaust air with intake air is vital for maintaining proper building pressure. When the amount of air leaving the building through exhaust systems matches the intake of outdoor air, it prevents common issues like drafts, mold growth, and unwanted air infiltration. This balance ensures indoor air quality, reduces energy waste, and keeps the HVAC system running smoothly and efficiently. Furthermore, managing these pressure conditions is vital for maintaining indoor air quality and ensuring comfort levels for occupants. Proper pressure balance ensures that air systems are working efficiently and that external pollutants drafts are minimized. This diagram showcases the airflow dynamics within a building equipped with a central exhaust fan. The central exhaust fan is responsible for removing stale air from the interior, creating negative air pressure, indicated by the blue arrows. This negative pressure draws fresh air into the space through various infiltration points, represented by the negative air pressure symbols. The positive air pressure, shown with the plus signs, indicates the direction of incoming air, which helps maintain a balanced and healthy indoor environment. Understanding this airflow system is crucial for effective ventilation, as it ensures the continuous exchange of air, improving indoor air quality while controlling humidity and odors. Dampers. Now let's move on to dampers. These are essential devices in HVAC systems that help regulate and control airflow. They're typically installed within the ductwork to adjust the amount of air flowing to specific areas. Firstly, dampers work by either opening and closing to control air volume depending on the pressure airflow requirements. This allows buildings to maintain proper ventilation and effective temperature regulation. Outside air damper. Let's now discuss the outside air damper. This device plays a key role in controlling how much fresh outdoor air enters the HVAC system. Firstly, Its job is to regulate the intake of outdoor air depending on the external conditions like temperature and humidity. This ensures that indoor air quality, IAQ, is maintained without excessive energy consumption. Furthermore, proper ventilation is critical because too little outdoor air can lead to stale air, while too much fresh air can result in unnecessary heating or cooling demands. Moreover, by controlling the flow of fresh air, outside air dampers improve energy efficiency by preventing the HVAC system from working harder than necessary. Relief air fans. Moving on, relief air fans are specialized fans that work with relief air dampers to regulate air pressure by expelling excess air from the system. Firstly, these fans operate when the HVAC system generates too much air pressure, helping to balance the system and maintain proper operation. They consume significantly less energy compared to return air fans because they only operate when there's excess pressure to manage. Additionally, relief air fans ensure that the HVAC system maintains optimal performance without unnecessary energy use. Unitary systems. Now let's talk about unitary systems. These are compact, self-contained HVAC solutions that combine both heating and cooling in one single unit. Firstly, they're perfect for smaller buildings, residential applications, individual zones within larger commercial buildings because they simplify system design and eliminate the need for separate components. Furthermore, they are space efficient since all necessary components are located in one unit. This means they're a great choice for situations where space is limited. Additionally, installing unitary systems is relatively easy because they don't require complex ductwork or additional external equipment. Split systems. Let's now focus on split systems. These are another popular option for HVAC applications. Firstly, split systems consist of two main components, an indoor air handler and an outdoor unit that contains the compressor and condenser. Component division. This division allows for more efficient use of space, with the noisy and bulky compressor and condenser situated outside, leaving only the air handler and ductwork inside the building. Multiple indoor units. Split systems are versatile in that they can accommodate multiple indoor units connected to one outdoor unit. This allows for decentralized temperature control, giving flexibility in large multi-zone buildings. Packaged systems. Finally, let's explore packaged systems. These are all-in-one HVAC solutions that combine components like the compressor, condenser, and evaporator into a single unit. Here's a breakdown of the components and how they function within the system. Compressor. The compressor is the heart of the HVAC system. It compresses refrigerant gas, raising its pressure and temperature, and sends it to the condenser. Condenser. The condenser cools the high-pressure refrigerant, causing it to condense from a gas to a liquid. This liquid refrigerant is then sent to the evaporator coil to absorb heat from the indoor air. Evaporator. The evaporator absorbs heat from the indoor air, causing the refrigerant to evaporate from a liquid to a gas. The air is then cooled and distributed back into the building via ductwork. Thank you for your time and attention throughout this presentation. We hope this session has provided you with valuable insights into HVAC systems, their components, and how they contribute to efficient, comfortable, and clean indoor environments. Next class, we will cover air and all-water HVAC systems, discussing their design, operation, and applications.